sequential percent changes. So this is about when we have percent increases and decreases following each other, when you combine percent increases and percent decreases. There are a few common mistakes involving percent increases and decreases, and the test loves to exploit these common oversights. They love to write problems where people make very predictable mistakes. These mistakes center on scenarios in which 2 or more percent changes follow in a sequence. For example, you might have a certain percent increase in a price, and then an employee will buy it with a certain percent employee discount. And so you have a percent up, a percent down. How do they combine? So for example, here's a typical problem. An item initially cost $100. At the beginning of the year, the price increased by 30%. After the increase, an employee purchased it with a 30% decrease, a 30% discount. What price did the employee pay? So pause the video right now, work on this on your own, and then restart the video when you're ready. The first thing I'll say is that the answer is not $100. That is the trap answer. That is the predictable mistake answer. More than half the people who take the test will guess that, and they will be wrong. That is the most common mistake in this whole subject. The same percent up and then down, or down and then up, does not put you back in the same place. People think, oh, a 30% up, 30% down, they cancel. They absolutely do not. You do not wind up back in the same place. We answer this using a product of multipliers. Though a 30% increase, that's a multiplier of 1.3. A 30% decrease is a multiplier of 0.7. And so we just multiply 100 by each one of those multipliers. So 100 times 1.3 times 0.7 gives us 91. And that's the actual price that the employee paid. Now this might be anti-intuitive for some people. Let's think about this. It starts out at 100. A 30% increase means it goes up to 130. Well, then the employee comes along with a 30% discount, but they're not getting a 30% discount on a price of 100. They're getting a 30% discount on a price of 130. And 30% of 130 is bigger than 30% of 100, which is why the amount it goes down is larger than the amount it goes up, which is why the employee winds up paying a price less than $100. Here's another problem. At the beginning of the year, the price of an item increased 30%. After the increase, an employee purchased it with a 40% discount. The price the employee paid was what percent below the original price? In other words, what percent below the price before the increase? So again, pause the video, take a moment to work this out on your own. The first thing I'll talk about here is the mistake. The common mistake, people are going to say, well, up 30%, then down 40%, 30 minus 40 is negative 10%, must be a 10% decrease. Guaranteed, more than half, maybe even 3/4 of the people who take the test will fall into this trap. It's as if the test writers just set up a huge butterfly net and people just run into it in hordes. It's absolutely 100% predictable how many people make this mistake. That's why it's so important to recognize this and understand not to make it. Whenever you have 2 or more percent changes in a row, never add or subtract the percents. That will always be wrong. You never want to add or subtract percent increases and decreases. Instead, what do? Of course, we use multipliers. We always use multipliers for percent increases and decreases. So a 30% increase, that's a 1.3 multiplier. A 40% decrease, that's a 0.6 multiplier. We're just going to multiply those two multipliers. They multiply to 0.78. 0.78 is the multiplier for a 22% decrease. And so this means that what we have going on here is a 22% decrease. The price that the employee paid was 22% less than the original price. Here's another. The price of a stock increased 20% in January, dropped 50% in February, and increased 40% in March. So in other words, that's the first quarter of the year. Find the percent change for this 3-month period, the percent change for the first quarter. So again, pause the video here and see if you can work this out. The first thing I'll say is that, of course, the mistake answer, the very predictable mistake that more than half the people who take the test will make, they're just going to do plus 30, minus 50, plus 40. That it gives us positive 10, so it must be a 10% increase. That's the mistake that people are going to make. Again, a very predictable mistake. The test writers absolutely love it when they can write a question that has such a predictable mistake. That's why it's so very important to understand the nature of this mistake so you don't fall into this trap. Of course, again, we're going to use multipliers. The multiplier for a 20% increase, 1.2. The multiplier for a 50% decline, that's 0.5. The multiplier for a 40% increase, 1.4. We're just going to multiply those three. To make things simple, I'm first going to multiply the last two. 0.5 or 1/2 times 1.4 will give me 0.7. And then 0.7 times 1.2 gives me 0.84. That is the multiplier for a 16% decrease. And so that's what's happened here. For the first quarter of the year, the stock decreased 16%. So in this topic, it's very important to understand both the nature of the mistakes, the very tempting mistakes, as well as to understand what the right thing is to do. Mistake number one, an increase and a decrease by the same percent do not get us back to the same original starting point. Mistake number two, in a series of percent changes, never add and subtract the individual percent. That will be wrong 100% of the time. Instead, what we're always going to do is figure out multipliers and multiply all the individual multipliers together. Simple and compound interest. This is one of my favorite topics here. Let's begin with simple interest. Well, simple interest is a mathematical fiction created to teach the idea of interest to grade school children. Absolutely no one in the real world uses simple interest. It is unlikely to appear on the test. With simple interest, the interest payment, the dollar amount of the interest payment, is exactly the same each time. So let's think about this. Bob deposits $1,000 in an account that yields 5% simple interest compounding annually. Well, 5% of $1,000 is $50. So what this really means is that every year, Bob is going to get another $50 worth of interest. So in the first year, $1,000 plus 50, we get $1,050. Then in the second year, we add $50 again. Then we add $50 again. And in each year, all we're doing is we're adding that same amount, $50. And so the account is rising by $50 each year. The exact same amount, dollar amount, is added each time. Simple interest pays interest only on the principal and not on the interest. Thus, the amount of interest accrued makes no difference to the interest payment, which is the same in each period. And indeed, as this graph shows, if we were to graph the amount in the account versus time, it would rise as a straight line. All that's happening each year is another $50 is being added, so that's why it rises at a constant slope. Simple interest is not often tested directly, but, and this is very important, it can be used for estimation purposes. And we'll talk about this more later in this video. The big idea of compound interest is interest on interest. In compound interest, we get the percent of interest paid on the total amount that has already accrued in the account, principal plus all previous interest payments. Thus, the more interest that has accrued, the larger the amount of the next interest payment. No two successive interest payments are ever the same, so the dollar amount is always different. The entire amount experiences the same percentage increase in each period. So that's what stays the same. It's not the dollar amount that stays the same, it's the percent increase that stays the same. That's what's going on in compound interest. So for example, Bob deposits $1,000 in an account that yields 5% interest compounding annually. So that means that every year, the amount in the account is going to experience a 5% increase. So it's going to get multiplied by 1.05, which is the multiplier for a 5% increase. So we start at $1,000. So construct that multiplier, 1.05, multiply by 1.05, we get 1050. Notice after 1 year that we get exactly the same amount, either with simple or compound interest, and that will always be the case if we're compounding annually, that after 1 year, one compounding period, simple interest and compound interest get exactly the same amount. After that, they diverge. So after 2 years, we multiply 1050 by this same multiplier. We get 1102.50, then multiply by that multiplier again and again. So these numbers are starting to get very hairy. So first of all, don't worry about getting these numbers by hand. You'd need a calculator to get these numbers. That's important thing number one. Important thing number two to notice is that, say after 4 years, simple interest would get up to $1,200. So here we have $1,215.50. We've done a little bit better than simple interest would do for us. Now, you might say, well, $15, what's the big deal about that? Well, think about it this way. Here we've only talked about 4 years. 4 years is a relatively short time in terms of investing, and we've only talked about a principal of $1,000. $1,000 is peanuts in terms of large-scale investing, and so you really have to think about this in terms of a more grand scale. With large amounts of money and or long periods of time, the difference between successive interest payments becomes substantial, and also the difference between the total amount gained with compound interest versus the total amount gained with simple interest becomes substantial. So big idea number one, compound interest always outperforms simple interest as long as there's more than 1 year. That is to say, as long as there's more than one compounding period. And this graph really summarizes it. The green line is the straight line of simple interest. The purple curve is the line of compound interest. Notice that it curves away from simple interest. It accelerates away from simple interest. So in the short term, it does a little bit better than simple interest, but then the longer we go, the more it diverges, and it does much, much better than simple interest does. By the end of this graph, notice that the compound interest total is over $1,000 more. That is the size of the principal. It's more than the size of the principal above the simple interest. Also notice, in Y years, the principal will be multiplied by the percent increase multiplier Y times. Let P be the principal and R be the multiplier. Then the total amount in the count after N years is P times the multiplier to the power of Y. We can even be a little more formal about this. Of course, if the annual percentage interest rate is I, then the multiplier for that, we change the interest to a decimal, that is divide by 100, and then add 1. That's how we get a percentage increase. So that's the multiplier for an I% increase. And of course, we're going to be multiplying by that Y times. Now here's what I'm going to say. I printed a formula here. Do not memorize this formula. That would be a big mistake. Instead, what I want you to do is understand the logic of how this formula was put together, and when you're doing a problem, rebuild the formula using that logic. Do not blindly memorize the result. So here's a formula, and I'll show what I mean. Sheila invests $4,000 in an account that yields 6% compounding annually for 8 years. What is the total amount after 8 years? So again, don't worry about getting the dollar amount. Just worry about getting the correct formula, the correct expression for the amount that would be in the account after 8 years. And I'll urge you to pause the video and try this on your own. So here's what I'll say. Here's how we'll approach this. The multiplier for a 6% increase, that's 1.06. It's going to get multiplied by that 8 times. So the total amount in the account is going to be 4,000 times that multiplier, 1.06 to the 8th. So that is the mathematical expression for the total amount in the account after 8 years. Now, of course, no one's going to expect you to calculate this without a calculator, but keep in mind that the test may not be asking for actual dollar amounts. The test may well list answer choices that are in this form. Certain amount times some decimal to some power, and then you have to recognize this particular one as the right answer. So sometimes the test actually does that, and just knowing how to construct the formula is enough to get the answer. Things get more interesting when we change the compounding period. Banks always give an annual percentage interest, but they may compound quarterly or monthly or even daily. For any compounding period smaller than a year, we need n, where n is the number of times that compounding period would occur in the year. So for example, quarterly, that means n equals 4. We're compounding 4 times a year. Monthly, n equals 12. We're compounding 12 times a year. Daily is 365. We're compounding 365 times a year. Technically, we'd be compounding 365 days during a regular year and 366 during a leap year. Let's not even worry about that. The test is not going to get into the region where you have to worry about leap years versus regular years. That's not something the test is going to do to you. Suppose the bank pays 5% annual interest compounding quarterly. The bank does not pay us 5% each quarter. That's not what's going on. That would be unrealistically generous. Instead, the bank pays us 5% divided by 4, which is 1.25%. That's the percent each quarter. In general, if there are n compounding periods in the year, we divide the annual percentage increase by n to get the percent for each individual compounding period. So we divide by 4 for quarterly compounding, we divide by 12 for monthly compounding. The correct multiplier now would be the multiplier for a percent increase of I divided by n. So writing this out very algebraically, 1 plus I over 100n, that's our multiplier. In y years, there would be n compounding periods each year, or n times y in y years. And so it means that we're multiplying by that multiplier ny times. So the total formula is this. And again, do not memorize this formula. That would be an exceptionally bad idea. Instead, I want you to think through the logic of it and, as it were, rebuild this formula each time using the logic of the situation. That is true understanding. Here's another problem. If Susan invests $1,000 in an account that yields 5% annual, compounding quarterly, then how much does she have after 6 years? Again, don't worry about getting an exact dollar amount. Just see if you can build the correct formula. You can pause the video here and work on this. So the first thing I'll say is that 5% annual has to get divided by 4. So the quarterly percentage is 1.25%. The multiplier for that is 1.0125. So that's our multiplier. The amount in the account experiences that percent increase 4 times each year, or 24 times in 6 years. So we're multiplying by that multiplier 24 times. So the final amount will be the principal, $1,000, times that multiplier to the power of 24. Okay, so that's the expression. And again, if the problem is simply looking for building the correct formula, that's the correct formula. I'll also say that we could approximate this. Sometimes the test will want us to approximate. We can approximate using simple interest. So let's think about this. 5%, that's $50. So that means in 6 years, they'd get $50 6 times, $300. That means simple interest gives us $1,300. So we can estimate that the compounding interest over 6 years is going to be something slightly more than $1,300. Probably not going to be as large as $1,400. So that kind of gives us a ballpark range for how much interest we're going to accrue here. How does the size of the compounding period determine the interest earned over time? For this, we will need a large principal and a long amount of time. Let's say that the annual interest rate is 5%, the principal is $1 million, and the time is 20 years. So we're really pumping up both the amount that we're dealing with as well as the time to look at these subtle differences. So, on that scale, simple interest would give us $2 million after 20 years. Compounding annually would give us 2.6, And then we see the other numbers for compounding quarterly, monthly, daily, and hourly. Notice that as we up the compounding, the more and more compounding we do, the amount of total interest we get paid increases. As the compounding period decreases, the overall amount of interest earned increases. So that's a big idea also. You always do better with more compounding. In summary, we talked about simple interest, not very realistic, not likely to appear by itself, but an excellent approximation tool. We talked about compounding annually. Then we talked about compounding other periods, quarterly and monthly. One big idea is that compound interest always pays more than simple interest. That's a really important idea. That's important especially when you're using the simple interest approximation. And also it's important to know that more compounding periods give us more money.